Hi, and a very good evening. Before we begin, we would like to express our sincere gratitude to our lecturer for the guidance provided throughout the semester. Let me introduce you to our teammates, which is first me, Justin, we got Rashwin, and Udaya. So, today we are presenting our work on digital filter design, specifically focusing on the removal of main humps from audio signal as an expansion for our Lab 5 experiments. So, our project builds upon the foundation laid during the original lab session. In that scenario, we provided with a file called Mystery Signal 1, which contained a speech contaminated by an unwanted high frequency noise. By using a spectrum analyzer, we identified a very sharp interference which were located specifically at 7.35 kilohertz. To resolve this, we implemented a notch filter, also known as a band stop filter. We also targeted a center frequency of 7350 Hz and a bandwidth of 200 Hz. This successfully excited the noise, leaving behind a clear, intelligible speech signal. So, to understand why this was effective, we must look at the characteristic of a notch filter. It is a specified type of band stop filter designed to reject a very narrow range of frequencies while allowing all others to pass through unaffected. It is the ideal tool for removing specific interference such as power line main humps, which is typically occurs at 50 Hz or 60 Hz, without damaging the integrity of the rest of the signal. Beyond audio speeds, these filters are critical in telecommunications, medical instrumentation like ECGs and EEGs, and various control systems. This fundamental concept serves as a bridge to our expansion project where we move from high frequency noise removal to addressing low frequency main humps. So that's it for me. Let me pass to the next person. Thank you.
Good day, everyone. My name is Rashwin, and my matrix number is B122310346. And I'll be talking about the expansion. So, what I'll be talking about is what is the expansion I did from the lab that we have chosen, which is Lab 5. So, the scenario is our microphones often pick up low frequency hums from nearby power lines, which in our country is around 50 hertz. So the challenge is, unlike the lab's frequency noise, which is 7.35 kilohertz, this expansion addresses low frequency noise, 50 hertz, which is not in the lab at all. So the strategy change is, normally in the lab, uh, we use a low pass filter to handle high frequency noise, but the expansion is now that we're going to use a high pass filter to try to address a low frequency noise, which was not done in the lab. Okay, so for the next part is signal generation. So in MATLAB, I've set a code to first it sets up a recording. Secondly, it records the user's voice. Third, it creates a 50 hertz hum, and then it mixes up them and saves it to the computer. So for the recording part, it records up to 5 seconds of audio. So let's say if I were to say my favorite hobby is swimming, so it records the audio and it saves it. After that, it generates a noise which is up to a 50 hertz sine wave. So it's difficult for us to authentically and accurately get a 50 hertz sound. So we mathematically added it into the code. So it adds a 50 hertz hum as well. After that, the mixing, the voice that you recorded, and the 50 hertz gets combined together. So the output would be whatever your recording is for the 5 seconds, and also a 50 hertz hum. So the audio would sound very noisy. Okay, for the Simulink implementation, the input block I've set up a multimedia file block. This is to load the audio that was mixed with the 50 hertz, which is a noisy audio, into the frame. And next is I have placed two spectrum analyzers for before and after. So the first spectrum analyzer will show the output and the graph of the noisy audio, and the after would show once the noise is removed, how would the graph look like. And then I've also added a manual switch to toggle between the noisy and the clean audio for a real-time comparison. So here are the results, the before filter and after filter. So as you can see, the before filter, the wave shows the audio that I recorded. So as you can see, there's a huge spike in the wave. So the spike is the 50 hertz sine wave noise that we added. Okay, so before the filter, it's a bit difficult to hear the audio properly because it's very noisy. So the voice is not clear. So after the filter, as you can see, as the audio is being played, the spike immediately goes down and is not detected. So when the audio plays, the noise is completely gone and the audio will play smoothly.
Hello, I'm Uttarajan Alakiravi, and now I'll talk about the filter design specifications. To address the interference in our audio signal, we developed a specific digital filter tailored to isolate the human voice from the background electrical noise. We choose high pass response specifically to cut out low frequency interference while allowing a higher voice frequency to pass through unimpeded. For the design method, we selected an IRR butterworth. This is chosen for its maximally flat passband, meaning it won't introduce unwanted ripples or distortions to the voice once it is clear and the cutoff point. Looking at our frequency setting, we set the stop frequency at 60 Hz. This ensures we heavily attenuate the common 50 Hz main hum caused by electrical equipment. The pass frequency was set to 100 kHz to ensure that the natural richness of human voice remains unaffected. To achieve a sharp enough transition between these 2 points, we implemented a high complexity 15th order structure using 8-second order sections. Moving on to the results, the difference before and after the filter was day and night. Before filtering, our spectrum analyzer showed a distinct high amplitude spike at 50 Hz. Subjectively, this made the audio sound muddy and quite irritating due to constant loud buzz. After applying the filter, the output showed a completely flat response at that 50 Hz mark, indicating the spike was effectively eliminated. The audio quality improved significantly and the playback became crisp. The voice was highly intelligible and the hum was gone. A common question in this design is why a high pass filter instead of a simple notch filter? While a notch filter targets one specific frequency, main hums often create harmonics at 100 Hz to 150 Hz. By using a high pass filter starting at 100 Hz, we don't just kill the primary hum, we clean up the entire low end basement for much cleaner overall vocal track. In conclusion, this assignment successfully demonstrated the universal power of digital signal processing technique. By identifying specific noise frequencies and designing targeted digital filters, we can solve a very specific audio degradation issue. We provide the inherent flexibility of digital design by adapting Simulink and the filtered design block. Tools often used for high frequency communications to solve low frequency audio tasks. Ultimately, these methods are not just theoretical exercises, They are highly effective, flexible tools for solving diverse real world audio problems. Once again, we shall thank Dr. David Ian Foster to guide us throughout this entire digital signal processing course. And thank you very much, sir, for your patience. And thank you very much, everyone, for your collaboration.